Hi, I'm Professor Wayne Miller, and this is a video for my course on science and religion. And this particular video is about the scientific revolution of the 17th century. Um, Science in the Middle Ages was mostly based upon the writings of Aristotle to a large degree. Uh, the greatest minds of the ancient world, at least in Europe, were probably the Greek philosophers, most notably Plato and Aristotle. Plato was the disciple of, or the student of Socrates, who never wrote anything, but Plato wrote many dialogues, and Aristotle was his student. And both Aristotle and Plato believed that everything that existed was a combination of form and matter. So you are matter and you have a form. But Plato was a bit of a mystic, and he felt that the physical world, the world of sensation, was not the real world. He believed that anything which is truly real had to be perfect and eternal. So he believed that the physical world was kind of a shadow world, that the physical world was just a bag of stuff, and all the things in this world are like shadowy reflections of our ideal forms, which exist in another world, which he called the topos noitos, or the place of cognition. So this world was the place of sensation, the physical world, but the world of cognition, the topos noitos, is the place where things existed in their real, true, eternal form. And so he believed that things pre-existed their birth in this world, and will exist after their death back in that world. And Plato believed, that if you wanted to understand anything, you had to meditate about it. You had to meditate about its original ideal form. So in the ideal world, the ideal topos noitos, in that world there is an ideal table. And that table has all the elements of tableness. Anything you could imagine about a table. There's a table there like that in that world. And if you meditate on it, you would know what the table is. And the same thing for a tree or a dog or a horse or anything. You meditate on the original form, and this will help you to understand what a thing is and what its purpose is. Now, his student Aristotle agreed that everything that exists is a combination of form and matter. But Aristotle is known to have said that he never saw any form without matter, or any matter without form. He believed you could not have form without matter. So he did not believe the way to understand something was to meditate about its ideal form. He said that the best way to understand anything is to observe it and analyze it. So that's why, to a large degree, Aristotle was considered the father of science, because he wanted to observe everything and understand everything. And so he wrote a lot about this, wrote a lot about everything. And he was known for his interest in philosophy, mathematics, politics, biology, anything that could be studied, he wanted to study it. And so for that reason, he's actually, in a sense, the father of science, because he really believed in observing things in the physical world. Now, Aristotle was not that concerned about what caused certain things to do certain things or behave in a certain way. What he was mostly concerned about is what was the ultimate purpose of things. He had a list of four causes, four types of causation that he said explained why things are the way they are. And these are the four. First of all, he said there's the material cause. And the material cause means, what is a thing made out of? So let's go back to the table. The material cause of a table is the wood. Wood is what you make a table from, so that's the material cause. The second cause he wanted to examine was the formal cause. In other words, what is the structure, the shape, what is the blueprint for something? What makes it the way it is? That's the formal cause. So if you were making a table, you'd have a diagram maybe of how you wanted it to look, how you wanted it to look, and that's the formal cause. Then there's the efficient cause, which he means the proximate cause, the thing that immediately causes the thing to exist, to come to be. So in the case of a table, it would be the carpenter who made the table. He is the efficient cause, or she is the efficient cause of the table. But for Aristotle, the most important cause of anything is what he called the final cause, in other words, the end cause, the end purpose, or in Greek it's telos, T-E-L-O-S. That's where we get the word telephone, telegraph, television, where you're talking or seeing over a distance. It's because telos means the ultimate end goal or purpose. So for Aristotle, he wasn't that concerned about what caused things to move or what acted on things, but what was their ultimate purpose. So when he was discussing gravity, he said that things fall down because they're heavy, and that's what heavy things do. They fall down, and light things go up. So fire goes up, and the earth is down, and heavy things go down. And that's so when you throw a ball, it goes and then it comes to rest because that's its purpose is to come to rest because it's heavy and it seeks to come to a low place where it can rest. So Aristotle believed that heavy things fall more quickly than light things, and that the reason things fall is because that's what they're supposed to do. And when you throw a ball, the reason it comes to rest someplace is because that's its nature. That is its nature. So Aristotle was not concerned that much with things acting upon other things. He just thought everything had its purpose and its place, and once you identified how things acted or worked, that you understood them. Um, so the writings of Plato and Aristotle and the other Greek philosophers and other sages of the ancient world were kept in a library, probably in many libraries, but one in particular, the Library of Alexandria in Egypt, was a major place for storing the information from the ancient world. But for some reason, or many reasons, perhaps in the early years of the Roman Empire, up through like 400 AD, there were a lot of wars and fights and different things, and the Library of Alexandria eventually was basically destroyed, or its contents were destroyed. There's not a whole lot of agreement about exactly how it happened, but it happened. So, for many centuries, the writings of Plato and Aristotle and the other Greeks were lost. Then, in around 10 or 1100 AD, the Crusades happened, and they were probably quite unfortunate by and large. But one good outcome of the Crusades was that following the Crusades, when they finished, there was much more trade between Europe and the Middle East. And what people found was that the writings of Plato and Aristotle and the other Greek philosophers were actually still maintained in the Arab world. And so these writings became available in Europe. And they eventually led to or contributed to the rise of the Renaissance. But anyway, in the 1200s, Thomas Aquinas was a very famous theologian for the Christian Church, the Catholic Church, and he read the writings of Aristotle, really liked them, and incorporated them into his Christian theology. And so the theories, the theories of Aristotle became prominent and predominant in European culture. In those days, there was very little distinction between philosophy and science. Philosophy and science were the same thing to a large degree, and theology was just another branch. And so, because Thomas Aquinas was very influential, his sort of promotion of Aristotle's ideas really had a tremendous effect in Europe. So a lot of people just accepted Aristotle's views on physics and how things worked. But eventually, I should also mention that the Greeks were very interested in the concept of perfection, and they believed that the universe uh, operated on perfect circles, that the Earth was the center of the universe, and all the planets and stars revolved around the Earth in perfect circles. And this is because they believed in the perfection of the universe. They also believed in a creator. They believed that a rational creator had created the universe. Aristotle called it the prime mover or the unmoved mover, and he felt that the origin of the universe was some perfect being, and our goal in life is to eventually attain that perfection of mind. That was his thought, and Plato as well. Uh, so they believed that the Earth was the center and that everything revolved around the Earth in perfect circles. And this became incorporated in Western culture through an astronomer named Ptolemy back in the second century. And that Ptolemaic view of the geocentric vision of the solar system and the universe held sway for many, many centuries, up through the 1500s. Finally, in the late 15, early 1600s, you have Copernicus who came along and said, hey, you know what? I've looked at the stars and they don't seem to be traveling around the Earth. I think that the planets, at least, are revolving around the sun. Now, he might have gotten in trouble with the church because that was not the church's position. But fortunately or unfortunately, he died before anybody could get upset with him. But his ideas were spread around. And one of the people who really liked his ideas was Galileo from Italy. And Galileo said, I have looked at the. In fact, Galileo made the first telescope, the refracting telescope. And Galileo said, I've looked at the planets, and they don't seem to be revolving around the Earth. They seem to be revolving around the sun. And furthermore, he saw the moon and saw that it was pockmarked with craters and stuff. He said, obviously, the celestial things in the sky there are not perfect orbs. They're not perfect circles or perfect spheres. They're not perfect at all in that sense. And also, he saw the moons of Jupiter and said, hey, obviously, if there are moons going around Jupiter, that means there's not everything's revolving around the Earth. So he liked Copernicus's idea that the sun was the center. On top of that, he really believed that you shouldn't just do science by accepting things on the basis of authority. You should check it out. Question authority and find out if the authorities are correct. So what he did was he decided to check on some of Aristotle's ideas, not just where the sun, whether we went around the sun or the earth or whatever, but he thought his ideas about gravity seemed, he wasn't quite sure that Aristotle was right. Now, they didn't have stopwatches in those days, so he couldn't go someplace and drop things. There's a story about him dropping things off the Leaning Tower of Pisa. I don't know if that's true or not, but the point is, he decided if my watch, I don't have a watch that can do things really quickly, but if I can slow gravity down, I can measure it more carefully. So what he did was to slow gravity down, in a sense, he made inclined planes, very flat boards that were facing each other. And he would roll a ball down one, and now Aristotle would say it would just come to rest at the bottom because that's what it does. But it turns out, no, it doesn't. When they're touching, the ball goes down one and it goes up the other to the same height, or nearly the same height as the first one. And Galileo found that by polishing the boards and making them very smooth, with very little friction, then the ball would go down and travel up to almost exactly the same height as its starting point. In other words, it didn't stop simply because it was meant to stop. What stopped it or slowed it down was friction. It was rubbing on something, and that's what slowed it down. So first of all, there was a very major important fact that Galileo found, that things don't just stop for no reason. They stop because of some force which slows them down, friction or something which impedes them. He also then did experiments with different types of balls or different types of things, rocks, metal, wood, whatever. And he found that things fell down at the same speed. It didn't matter what they weighed. It had nothing to do with the mass. It had to do only with the fact that gravity acts the same on everything. And so it didn't matter whether you're heavy or light. you fall at the same speed as anybody else. Now, obviously, people measuring the difference between rocks and feathers would say that, oh, the feathers are light, they don't fall. But that's because of air resistance. And this is what Galileo discovered, that things don't slow down for no reason. So this was a big thing to him, that momentum or impetus is important because things keep going unless something slows them down. That was a big thing. And so this was, there are other people who had done a few things in this area, but Galileo was the one who was most consistent to really use mathematics and experimentation, observation. This was something that the ancients did not do. They observed things and they did use mathematics to some degree, but they didn't exactly measure things the way he did. They didn't make little experiments to see if their measurements were correct or their theories are correct. Galileo did. And this was a huge beginning. This was a major step forward in the scientific revolution. He did have one problem though, because he did not. He liked the Copernicus idea that the planets revolved around the sun, but there were still problems when you looked at the sky, and some of the numbers didn't figure out quite right. But Johannes Kepler, who was a German astronomer, lived roughly the same time as Galileo. He used Galileo's telescope and made a better one, and he discovered that the planets, the reason their orbits don't line up with circles is because they're not circles. They're actually ellipses, elongated circles. And this was very big deal, and people who studied this were shocked to find this out, because they were still going on the idea that the heavenly objects are all perfect spheres or perfect circles. Then, a bit later in the 17th century, Isaac Newton was born, and he was very, very, very. He wasn't a party animal. Let's put it that way. He was very introverted and very studious, and he got really interested in alchemy and astronomy, and he wanted to. He believed, as did Galileo, he believed in God very firmly, and they believed that because there's a God, because they believed in God, and they believed that God was a rational creator, they believed that the universe was rational, rationally organized, and could be understood through mathematics. So he basically took off where Galileo started and went further and said, hey, I want to understand the universe mathematically. And so there's a story about him seeing an apple fall and saying, hey, if the apple's falling, isn't the moon and the earth don't they have the same attraction as the apple and the earth? We don't know how accurate that story is, but anyway, he thought about these things, and eventually it led him to the point where he said gravity in the heavens and gravity on earth are the same thing. And he was able to develop, formulate the law of gravity. The force of gravity is based on a gravitational constant and times the mass of the two objects who are interacting with each other over the radius squared of the separation between them. Anyway, this is the point is he developed a law of gravity. He also worked beyond what Galileo had done and said, well, there are several laws of motion. There are at least three. One is that the acceleration of any object depends upon the force and the mass. So this is where, if you've studied physics, you hear the phrase F equals ma, the mathematical phrase F equals ma means the force that needed to move anything depends on the mass times the acceleration you want to achieve. Or if you want to do it the other way, you can say the acceleration depends upon the force divided by the mass. But anyway, he also said that, going back to inertia, that not only do things not slow down without some sort of force acting on them, they don't move without some force acting on them. So in other words, everything either stays at rest until a force acts on it to move it, or things which are moving stay in the same direction, the same velocity, until some force acts on them to change direction or slow them down. So that was the second law of motion. And the third was that for every action, there's an equal and opposite reaction. And that's why rockets could go, because in a rocket, you have a chamber with fuel which explodes, and part of it goes out the back, pushes out the back of the rocket, and the other part, the opposite of that, it pushes up into the rocket and causes it to blast off from the Earth. So what's really important, and also that Isaac Newton was, in fact, probably the smartest scientific mind in history. The reason I say that is because not only did he discover the law of gravity, not only did he discover the three basic laws of motion, but when he was presented with the idea from Johannes Kepler that the planets, when it revolved, around the sun in elliptical orbits, he wanted to understand why is that so? How does that happen? How can we analyze that? In order to do that, he had to invent calculus, which he did. He invented differential and integral calculus in order to figure out how the planets move around the sun and around the earth, how the moon moves around the earth. So he invented calculus, and then he decided he hadn't done enough with the laws of gravity and the laws of motion and inventing calculus to find out about elliptical orbits. He also decided he wanted to know more about light, so he took a prism and held it up to a small beam of light in his room, and guess what? It came out many colors, right? The colors of the rainbow. But then you could take another prism and put those rainbow colors through it. It'll go back to white light. So this proved to people that, in fact, white light is a combination of many different colors. This was something which was mind-blowing at the time. And he did all this before he was 26 years old. So he was a very young man, and he just was a real, yeah, I guess you'd call him a real nerd in today's world. He was very studious and very eccentric in that regard. Uh, the main point here, if you listen to any of my other lectures, or even the lectures of Richard Feynman, where he talks about what is science, he said science is a belief in the ignorance of experts. Science does not depend upon bowing or accepting authority. When someone says something, it doesn't matter how authoritative they are, they have to show through experimentation and proof. You have to, take their idea, their theories, make predictions based on the theories, then test them and check the results with the prediction. And if the prediction does not line up with the experimental result, then the theory is no good. So you have to have a different theory. And this is what Galileo and then eventually, especially Newton, uh, brought to light, is that science is done by testing hypotheses and then checking to make sure that your hypothesis is right. And then you can make up, very elegant mathematical formulae to explain why it works this way and how it works this way, so you can make predictions about other things. And one of the things that Feynman said in some of his lectures is it's astonishing that Newton's ideas have held up for 300 years. From 1600s to the 1900s, this was it. I mean, everything. And even today, the ideas of Newton, Newtonian physics, are basically, they cover everything that we encounter in daily life, 99.9%. It's only when you get into, speed of light and things like this, where and why Mercury acts a different way than you think it should. These things, on the very edges of what science that you would encounter normally, yeah, we needed quantum physics or Einstein's theory of relativity to explain to us how things work in those extreme edges. But for 99.9% of everything we encounter today, Newtonian physics is still accurate. And this is astonishing because people have tested it over and over and over again, and it still comes out to be accurate. So this was the great scientific revolution of the 17th century. And everything that we have today in terms of science and technology exists because of Galileo, and especially because of Newton. They without them, we would not have the technological world that we have today. And the thing I want to point out is that they believed they could find answers. They could make very accurate predictions about things because they believed in God. They believed that there was a rational creator and the universe was rationally organized. And by thinking about it and experimenting and observing, you could actually discover what the fundamental laws and principles of the universe are. So even today, when scientists say they don't believe in God or they're agnostic or atheist, but the point is, if they were truly nihilistic and didn't believe in anything, it would be very hard to be a scientist because then why would you think that you could discover anything? If everything is just chaos, then what can you discover other than, well, everything's chaos? We can't predict anything. So even in quantum physics, physicists today may not understand why things happen the way they do on a really subatomic level, but they know that things are consistent and you can make predictions about how things are going to work if you do enough mathematics. So this is very interesting that sometimes the people who claim to be agnostic are actually more religious than the religious people because they actually believe that the universe is rational and comprehensible. So anyway, I think this is very important to understand, and it's very important even today to understand that science does not prove or disprove God. Science, as Feynman said, makes probabilities. And I think that if we look at the as we dig deeper and deeper and deeper into the nature of reality, we're going to find out that things are very, very, very precise and complicated. And then that leaves us with the question is, how can things be so complex and so intricate and yet work so beautifully if the universe is simply random chaos? Um, this is a question I want to leave you with as we study science and religion. And I hope you will take to heart the findings of Isaac Newton and Galileo and also the statements of Richard Feynman, who said science is a belief in the ignorance of experts, that we need to check and recheck and study and recheck what people claim to have proved. All right. Um, there is a there was a Peanuts comic some time ago. People were talking about we have to just trust the science, and Linus says, "What do you mean trust the science? That's the most unscientific thing I've ever heard. Questioning science is how you do science." And that's still true today, and it's always true. We will not advance scientifically if we just accept somebody's word because they're an authority figure. No, we have to check. Everything has to be checked and tested. So thank you for listening. Please have a great day and a great. Hope you enjoy this lecture. Thank you. Bye bye.